Okay, so thank you everyone. Today we have Haruka from Masafumi's lab, and she will giving a talk on the quality, the structure of some kind of emotion experience, and based on various types of measurement. Yeah, I think that's enough. Yeah, and Haruka,
Thank you so much.
if you have anything to add on, you're free to go ahead and just start your.
Okay, can you see the slides?
Yes.
Thank you. Okay, let's begin my talk. Uh, okay, I'd like to begin my presentation titled Correspondence of High-Dimensional Emotion Structure Elicited from Video Collabs Between Humans and Multimodal LLMs. We humans experience a wide range of complex emotions in our daily lives. To better understand these emotions, a variety of classification systems and theoretical models have been proposed over the years. Classical emotion theories aims to reduce the complexity into simpler structure. For example, the dimensional approach suggests that all emotions can be mapped onto two-dimensional space defined by valence and arousal. Another well-known theory is a basic emotion theory, which posits that human emotions can be broken down into a set of 6 core types, such as joy or sad or something else. However, more recent research suggests that human emotions are far complex and high-dimensional, and that such low-dimensional models may not be however, more research suggests that human emotions are far complex and high-dimensional. For instance, Cohen and Kelton in 2017 analyzed self-reported emotions while participants watched video clips and found the human emotional experience spanned at least 27 distinct dimensions. For instance, Cohen and Kelton in 2017 analyzed self-reported emotions while participants watched video clips and found that human emotional experience spanned at least 27 distinct dimensions. Against this background, growing attention has been directed toward multimodal large language models, MLLMs. MLLMs are AI models that can process not only text but also multiple modalities such as images and audio. These models have rapidly advanced in recent years. They have already demonstrated strong performance in tasks involving external emotional experiences. For example, sentiment analysis, which infers emotions from textual content, and facial expression recognition, which detects emotions based on facial features. These are both widely known and practically applied today. If LLMs could go beyond these surface-level tasks and begin to replicate the internal emotional responses that humans experience when exposed to complex multimodal stimuli such as videos, they could become powerful new tools for emotion research. However, whether MLMs can truly predict the internal emotional experience of humans, such as the subjective feelings we have while watching videos, remains an open question. This is a challenging task because it requires not just feature extraction, but multi-step reasoning. Specifically, in order to predict how a person feels while watching video, an MLM must first accurately recognize what is visually depicted, and then infer how the viewer is likely to interpret and emotionally respond to it based on contextual and background knowledge. Let me show you an example.
Can I ask just a quick question?
Yeah.
This is sort of like your hypothesis, right?
Yeah, this is a hypothesis, I think.
Okay.
Yeah.
Because I'm thinking that, this is not necessarily the case even for the human version of the emotion experience. Sometimes you don't know what you're seeing, but you can feel like a fear or something as well, right?
Yeah.
Oh, yeah. Just
So,
I just make sure. Okay.
Okay, thank you. This is an example video. This is a short horror clip in which a girl inside a painting slightly moves and turns to face the viewers only when she look away. Nothing dangerous or violent actually happens on screen, and yet viewers often experience intense fear simply due to the anticipation and tension that builds in that moment. Such emotional experience cannot be explained by the visual features alone. They arise from the narrative context, the viewer's prior knowledge of horror tropes, and the psychological discomfort caused by a mismatch between memory and perception. In this case, realizing that something you thought was still has suddenly moved. In other words, these kinds of context-dependent, internally experienced emotions cannot be captured by simply analyzing external facial expressions or surface level cues. So predicting how someone will feel while watching a video is not a simple image recognition task. It demands not a simple image recognition task. It demands high-level layered reasoning, making it a substantial challenge for MLLMs. In this study, we investigate to what extent MLLMs can accurately predict the human emotion structures when watching videos. This task is particularly challenging for two main reasons. First, the target emotions themselves have a complex structure which goes beyond simple classification. Second, it requires MLLMs to perform multi-step reasoning in order to interpret the emotional impact of complex stimuli. In this experiment, we used a large-scale dataset of human emotions elicited during video viewing. To capture subtle emotional nuances, we used 80 distinct emotion categories for the ratings. We then compared the emotions reported by human participants while watching a video with emotions predicted by the model when given the same video as input. The videos and human emotion rating data were taken from Koide Majima et al. 2020, published in Neuroimage. As a control to evaluate the model's estimation accuracy, we also compared the consistency of emotion reports between two separated groups of human participants.
Just another quick question now.
Yeah.
Even though this schematic actually implies that everybody is watching at the same video, it's not probably true, right?
Everyone watched the same video.
At the same time, like a movie theater?
No. In labo, and each person.
Okay.
Yeah.
Francesco.
Yes. Can you say more about what do you mean by emotion intensity? Is just to understand what's going on. Is the participant that rate that specific emotion according to that specific clip, or this is a scale on how you define the emotional state?
Okay, I will explain the next slide.
Oh, sorry.
Okay.
Wait,
The
before that, Kyoko, is that a short question or clarification?
Yeah, it's clarification. So how did you select the candidate emotions like fear and thrill and grief, relief, joy and shock?
Okay. The author said that they research what kind of emotion term exists, and they picked up 80 categories.
Okay.
So yeah.
Thank you.
Are they from Cohen and Keltner's paper? I mean,
No.
the categories?
This word is not from Cohen and Keltner categories. They
It's a different study.
Different set, okay.
yeah, different emotion categories
Dimension.
from Cohen Keltner.
Okay.
Is there any question?
It's all right for now.
Okay. Okay, I explain the data of humans. The human data used in this study consists of emotion ratings that participants gave while watching video clips. For each emotion category, 4 different participants were assigned to rate how strongly they felt that emotion. They used the scale from 0, meaning not felt at all, to 100, meaning felt very strongly. While watching each video, participants continuously rated their feelings every second. These values were then averaged over time to produce a final score for each video. In total, we obtained emotion ratings for 50, 100, and 50 videos across 80 distinct emotion categories. And as a model, we used Gemini 2.0/001 as a multimodal large language model. By inputting both the video and this prompt, we asked the model to estimate the 80 emotion categories reported by human participants. Importantly, we did not fine-tune Gemini. All instructions were given through prompting alone. We conducted our analysis on the 550 videos. Participants are all Japanese, so prompts are translated into Japanese. For example, when showing the kind of video, both human and LLMs tend to rate cuteness as high and anger as low. In this way, we present a variety of videos, and both the model and human participants rate each video across multiple emotion categories. As a result, we obtain a table where emotion categories are rows and videos are video IDs are columns. This table serves as a basis for further analysis from multiple perspectives. First, as a simple and intuitive analysis, we calculated the correlation coefficient between human and model Gemini ratings for each video. The purpose of this analysis was to assess how well Gemini predicts human emotions based on video-wise similarity. This histogram summarizes the Pearson correlation coefficient between human and Gemini emotion ratings for each video. The average correlation is 0.3374, indicating that Gemini is able to reproduce human emotion to a reasonable degree. As a point of comparison, the average intergroup correlation among human participants was 0.313. This suggests that the model predicts are surprisingly close to those of actual humans, at least in terms of video-wise emotional similarity.
Sorry,
Okay.
about this. So when you compare the human to Gemini, you average the rating across people.
Yeah.
And then that to Gemini. And then group 1 and group 2 is also first average within group 1 and the group 2, and
Yes.
then take the average.
Yeah.
Oh. And 0 point minus. Okay, all right, thank you.
Thank you. Any question?
That's fine.
All right. Okay.
Francesco?
Yes, it's a methodological question, so maybe if it's too long, the answer, we can discuss it later. But previously you said that you used Gemini 2.0 Flash, correct?
Sorry, one more, please.
Sorry, you said you used Gemini 2.0 Flash.
2.0. Yeah.
Okay. So my question is, if I remember correctly, Gemini 2.0 should have some sort of large context window, like meaning that he remembers or he learns from various conversations you had with him. So my question is how, like, of course, this risk that after you ask 100 questions, the 101 is biased, right? And so my question is if you consider that, or if there are ways to work around it, like asking the question with, I don't know, different accounts or something.
Thank you. Thank you for a question. I use Gemini by API. So
Yes.
the recording is not exists. So yeah, there's no interruption.
Okay, so if you do it by API, you don't interfere with each question, basically. Okay, sorry, I didn't know that.
Kyoko, you had some correct. Okay, that's fine. All right.
Okay. This is the first result. And yeah, these results suggest that MLMs are able to estimate human emotions in terms of the similarity of emotional responses across videos. However, this evaluation method has several limitations. This evaluation allows us to assess how similar the model's emotion ratings are to human ratings for each individual video. However, it doesn't take into account the emotional similarity across different videos. For example, a video where someone plays with a pet and another where someone receives a gift may different content, but both tend to evoke similar positive emotions. In contrast, horror video that induce fear will likely produce a very different emotional experience. Such relationships, the emotional similarity or distance between different videos, in other words, emotional structure, are not captured by the previous evaluation approach. So we further evaluated whether Gemini could also replicate the relationship between relational structure among emotions evoked by different videos. Under this background, we used a method called representation similarity analysis, RSA. First, we constructed the similarity matrices for both human and Gemini. For each pair of videos, such as video 0 and video 1, or video 0 to video 2, we computed the dissimilarity in their emotion ratings. Then we calculated the correlation between the two matrices to assess how well the model's emotional structure aligns with that of humans. Here are the results of RSA. These figures show the dissimilarity matrices created from the emotional ratings of humans and Gemini. Both the vertical and horizontal axes represent video IDs, and each pixel indicates the emotional dissimilarity between a pair of videos. Bright pixels represent higher similarity, and darker pixels indicate lower similarity. The RSA similarity, the correlation between the dissimilarity matrices of human and Gemini was 0.558, indicating that Gemini was able to capture the overall emotion structure for indicating that Gemini was able to capture the human emotion structure for human emotion structure responses to a moderate degree. For reference, the RSA value between two groups of human participants was 0.859. Although the model Gemini does not reach the level of agreement observed between humans, it still demonstrates a fairly strong approximation of human emotion structure.
Kyoko.
I haven't used RSA before, so could you tell me what range of values would indicate that the two items are considered similar or different?
Okay. The RSA value 0 means there's no similarity, and 1 is the max similarity.
And
did you use 1 minus r square root of r minus r?
Yeah, 1 minus r. So to make this similarity matrix, I used 1 minus cosine similarity between a pair of videos.
Cosine similarity. Okay.
Yes.
I see.
so 0.
William. Yeah. Sorry. Kyoko, continue.
I'm sorry. So 0.5 RSA similarity is high or not? So this interpretation could be difficult, I think.
Okay. I think this value is high because the past model before Gemini, I conducted the same analysis, and the RSA value was 0.2 or 0.1. So compared that such kind of videos, this value is high.
So it's improved.
Yes.
With other models.
Yeah.
But compared to human versus human, it's relatively low.
Yeah.
And in the context of statistical mathematics, which value is considered to be high? What I wanted to ask you is this one.
I think it is very hard question, and I don't know which value is good. So
you need some kind of a bootstrap or some kind of non-parametric analysis to do that. Maybe if you don't have the answer, maybe we can talk about it later.
Yeah, thank you.
William.
Yes. So could you clarify what exactly is the difference in the way you calculated the results for this result number 2 and the earlier one?
The difference. What is the difference between this?
Yes.
This results. As I mentioned, this in this histogram cannot consider the similarity between different videos. This in the first result, we only evaluate the similarity of video 1 and 1, and video 1 and video 2 and 2. Only this. We evaluate only this correspondence. But in the analysis RSA is the analysis of RSA, we can consider the relationship between video 1 and 2, or 1 and 3, or 1 and 100. We can compare the relationship between we can consider the relationship between two videos. This is the difference between the analysis of histogram or RSA, I think.
I see, thank you.
Yeah, in a given pair, the same pair, how similar the rating pattern is, that's the analysis 1. And the analysis 2 is a pattern of the similarity or dissimilarity, whether that itself is different or similar, right? Yeah, and then there is a question from Zoe. Do you want to speak or should I read it?
It was mostly a comment. But for going back to Kyoko's question about what level of correlation is meaningfully high, if you haven't already done this, I might suggest looking into noise ceiling. So like, what is the correlation, like max correlation that you could get when you like randomly correlate between people? I think, yeah, so if you do that, then you get like a baseline number. And then if you get some value beyond that, then you can kind of confidently say that this is a meaningfully high correlation. So I might, and then like now said, you could do some kind of bootstrapping method. And it seems like there are different ways to calculate noise ceiling, but I might use that. Yeah.
Oh, thank you so much. As a baseline, I also conducted a similar analysis. So as a control, I shuffled the rating. I shuffled the all table I shuffled the value of this table and the same. I conducted same analysis as a control, and the RSA value was maybe around 0. So as a baseline, I conducted the shuffled. I conducted the shuffle analysis, and the RSA value was around 0. So I think the RSA similarity of this value is high, I think.
Significantly higher than 0. That's what you.
Yes,
and
yes,
then,
yes.
what Zoe was also suggesting was that maybe using this, RSA toolbox, there is a way to probably compute the significance from the maximally achievable similarity.
Oh.
I think that's what you meant, right, Zoe?
Can you repeat the term?
Maximally achievable similarity compared to maximally achievable similarity.
Yeah.
Yeah, but I think what she's showing is sort of like that, but maybe, yeah, I'll just, maybe we can talk about that in detail later, but yeah, Andres.
So you mentioned that you calculate dissimilarity using cosine.
1 minus.
1 minus cosine. So I was just wondering why you swapped from the correlation to cosine, the distance.
Your question is why this is 1?
No.
So here you constructed these matrices using the cosine distance, right?
Yeah.
previously you were showing the results using the correlation. So I just wondered why you swapped, like why you changed from correlation to cosine.
Why
Or-
change the color sign?
Yeah, in other words, what happens if you use 1 minus square root
Oh,
square root of 1 minus Pearson correlation or something like that, or square root, or something like that.
1 minus r.
1 minus r or anything, you know, just based on the correlation coefficient. If you do the same thing, would you get the same results?
yeah. Oh, yes, I think. Oh.
Did you do that already or no?
Oh, no, I didn't do that, I think.
Okay, and then while we're on this slide, I also noticed that, so is the human matrix the average across all your participants? The top left
sorry.
matrix. Is the top left matrix the average across
Mhm.
all your participants?
Yeah, all participants.
Because the participants group 1 and participants group 2 matrices, they look very similar,
Mhm.
but when you combine all your participants together, it looks like you get a pretty different matrix.
Ah,
Yeah, group 1 and
okay,
group 2.
okay.
Because the sorting is different, probably.
Yeah, so yeah, the sorting is not same.
Okay, thank you.
You are ordering the video IDs differently at the top,
Yes.
right?
Yeah, different. The ID is permutation.
But that I mean it's not good probably to do that because ID means identity.
Sorry. Okay.
Yeah, so same number should correspond to the same video.
Okay.
Yeah, in terms of word
Okay.
definition. Okay. Yeah, so Francisco's quick question is that the human is participants 1 plus 2, right?
Yeah, one plus 2.
Yes, but in a different order in terms of video IDs. Yes.
Yeah.
Okay.
Okay, I will go to the next explanation. Oh. So maybe this one. Okay. Okay. RS. Okay. So okay, I explain. The method we used, RSA is capable of evaluating relationship between emotions evoked by different videos. However, this method assumes a one-to-one correspondence between the emotions evoked in humans and those predicted by Gemini for each video. For example, as shown in this figure, it assumes that green cells correspond to each other, and likewise blue cells are corresponded and yellow cells are corresponded. In other words, it presumes that the emotional relationships Gemini infers for video 1 and video 2 to directly correspond to the relationship that human experience for those same 2 videos. So, however, from a more straightforward perspective, we should consider which human reported emotions Gemini's predicted emotions actually correspond to. So, as a final analysis, we directly examines the correspondence between the emotions predicted by Gemini and the emotions reported by humans. The analysis we used here is called Gromov-Wasserstein alignment or GW alignment. This method is based on optimal transport theory and aims to identify corresponding video pairs while preserving their relative similarity structure. Take a look at this figure. This diagram on the left shows an emotion structure where each icon represents a single video. When we align these two emotion structures using GW alignment, this matrix is the result. And this matrix represents that the dog video is matched with the cat video, and the skull video is matched with the ghost video. Meanwhile, the baby video and the insect video are each aligned with themselves. In this way, we use the transportation matrix to evaluate which videos correspond between the model and human emotion ratings. Here are the results of GW alignment between model, Gemini, and human emotion ratings. The left figure shows the results of these figures results of GW alignment. This left heat map visualizes the probability that a video from Gemini corresponds to a video from human ratings based on emotion structure. The vertical axis responds to the video IDs rated by humans, and the horizontal axis represents those rated by Gemini. Each pixel indicates the probability that a pair of videos are matched based on their emotional profiles. Darker colors indicate higher probability, while lighter colors indicate lower probability. If a clear diagonal line were present, it would mean that the model and human responses correspond 1-to-1. However, in this case, no clear diagonal pattern is visible in this heat map. The matching rate, defined as the proportion of correctly aligned pairs along the diagonal, is only 2.36%, indicating very low correspondence between Gemini and human responses. In contrast, the matching rate between two humans participants group was 16 and 36%, suggesting that humans share a highly consistent emotion structure. From this result, we can see that Gemini does not accurately reproduce the human emotion structure when evaluated on this matching basis. Is this is a very
there's several questions now. William first.
Yes, my question is the matching rate between human and Gemini, is that about equal to chance, or is that still higher than chance?
Chance level is 0.5%, so higher than the chance level.
Okay.
Yes.
And Genshin.
Yeah, so relatedly, I'm not sure how to interpret this 16.33% of matching rate. Does that mean only 16% of the videos from group 1 can be matched to the same videos on group 2?
Yeah.
Is that a good matching performance, or is it just good because it's much better than Gemini's performance?
Oh, sorry, one more, please.
So it's if only 16% of videos from participant group 1 are mapped to group 2, is that like is that considered to be like a generally very good matching?
Okay. In general, this rate is not high. In such as the research of colors, the matching rate is around 80%. So maybe you know, 80%. The matching rate is 80% in the research of color, but So comparing such kind of research, this matching rate is very low, I think. But the emotion is a very difficult task. So I think this percentage, 16% is surprisingly high, I think.
We can't really compare that, but because the method of evaluating similarity is also already very different. But Lipen, how much percentage did you get?
13.
13?
Yes, 13.
1, 3?
No.
30. 30. So the Lipen here, maybe we can talk about it later, but when we directly, get the similarity rating between the pairs of emotion stimuli, also very different stimulus set as well. We got like 30, 40% or so, right? Of the alignment, the matching.
Regarding
But Francesco, what was it? Follow-up question first.
So regarding this, I think part of the reason is that you are considering one-to-one correspondence here. But for emotions, we probably need to consider one-to-many correspondence.
Yeah, so maybe you are asking
so
for
if
something
you
like
have
that.
this results in the future, in later slides, I would stop here.
Yeah. Okay, Francesco.
Yes, sorry. So to be sure, I'm understanding this means that of the two structure, there is a perfect overlap between 16.36% of their points, right?
Oh, so sorry.
Not really overlap,
Hmm?
but matching correspondence.
So yeah, so it's but it's like perfect correspondence, right?
Not really. By what you mean by perfect is unclear, but you see that the probability is not 100. If that's what you mean by 100.
Yeah. Okay.
Among all the possible videos, this one had at the most like the weight is 0.002 or something.
Okay. Yeah, thank you.
I don't know whether what you mean by perfect is very unclear in this context, but yeah.
Yeah, no, I thought the dark point was yeah. Okay, makes sense. Yeah.
Lipen.
Yeah, just a clarify question. So this matching rate is top K and K equals 0. K equal 1. Oh, K equal 1. Then K.
No, wait. Is it? It's a top one matching rate, right?
Yes, top one matching rate.
So if it is top one matching rate, then it is very low in my case. Also 0 or nearly 0.
Nearly 0 in your case.
Yeah, even in typical versus typical.
Okay. So the number that we gave you was wrong. So in the real our data top one matching rate was like 1% or something.
Yeah.
Wow.
Very similar to that human and
Gemini. Okay.
Okay, let's move on to next. Okay. However, the one-to-one matching rate is this is a very strict evaluation criteria. Expecting Gemini to show exactly the same emotion, exactly same emotion for exactly the same video as a human is an extremely high bar. So next, we introduce a more relaxed evaluation, category matching. Here, instead of asking, does the model match the exact same video? We ask, does the model match a video that evokes a similar type of emotion. For example, in this emotional structure, we define two categories: videos evoked sense of cuteness, and videos that evoked fear. Under this approach, even cases where the matching rate was very low under the strict method now show 100% alignment as a category level. So the green line indicates the category boundary, and if the dot in the diagonal green box, the matching rate, the correct, we consider that this is correct. So if under this approach, even cases where the matching rate was very low under the strict method now show 100% alignment as the category level. In this way, category matching allows us to determine whether the model is completely wrong or if it is at least moving in the right direction. Here's the result of category matching. The matrix shown here is the same as before, but note that the evaluation criterion is different. In this figure, the green lines indicate category boundaries. If a dot appears within the boxes along the diagonal, it means that the video pairs is classified into the same category. We used 10 categories generated by applying k-means clustering to human emotion ratings. The results show that the category matching rate for the Gemini was 50.5%, while the rate between human participants, the category matching rate was 66.18%. This indicates that the model is not making completely random or irrelevant predictions, but rather provides a fairly reasonable estimation of human emotion structure. Here's a summary so far. In response, okay.
One more question, Lipen.
Yeah, how did you do the classification?
Okay. The classification. I generated the class applying k-means clustering to human emotion ratings. This part.
Okay, so you apply a classification method to only human data, and then use for both human and Gemini compared.
Yeah.
Okay.
Clustering, not a classification. So
hierarchical clustering.
K-means, right?
Yeah, k-means clustering.
And you request 10 clusters.
Yes.
Okay.
Here's the summary so far. In response to the question, how do the emotions estimated by Gemini correspond to those reported by humans? We found that they aligned well at the category level. This finding suggests that MLLMs can to some extent reproduce or replicate the complexity of human emotions. Replicates the complex human emotion structures. Finally, discussion. We compared videos where the Gemini successfully predict emotions with those where it failed. The model was particularly good at predicting emotions that do not heavily depend on context. For example, in this video, cats are depicted and the model straightforward estimates the emotions of cuteness. This suggests that when emotions can be determined primarily from clear visual cues, the model achieves high accuracy. On the other hand, in videos where the model failed, context and social cues played a crucial roles. Please see this video. Take this video. For example, a player attempts to a high five but gets ignored. Since other players in the background successfully complete their high fives, and the model predicted positive emotions such as admiration or joy. However, the appropriate emotions here is awkwardness. In such cases, MLMs fail to fully interpret the context, resulting in predictions that diverge from human judgments. This result indicates that the model performs well when emotions are driven by clear visual features and require little inference, but struggles when emotions depends on complex contextual reasoning. To summarize, we found that Gemini 2.0/001 can partially reconstruct human emotion structures. However, its accuracy is still far from perfect, and there is room for improvement. One likely reason is that the model struggles to fully capture complex contextual information. That concludes my presentation. Thank you for your attention.
Thank you. Thank you, Haruka. So maybe let's take a 5-minute break, and then if anybody has a question afterwards, let's discuss further details. Okay?
Okay.
All right. Thank you. Let's take a break for 5 minutes.
That's